Light, its properties, its nature, has always fascinated humanity because it's essential to life. There is also a reference to light in this famous engraving by Albrecht Dürer, where it appears as a rainbow in the background. This artwork from 1514, well before the scientific revolution, is one of the most important art pieces of its time. This may be because it's not immediately clear what it is about. Many interpretations of what Dürer is showing here have been offered. One way of looking at this engraving is to see it as a contemplation of the world, of nature, before the scientific revolution. An angel can be seen somewhat moody, maybe in deep thought. The angel may represent human genius, human curiosity. This is supported by the artifacts around the angel. The angel is surrounded by scattered tools of experimentation. A ruler can be seen, a compass, a plane, a hammer. They are scattered about. Furthermore, there are objects of scientific interest. A magic square behind the angel on the wall may represent mathematics. A polyhedron may represent space. An hourglass above the angel may be representing time. A scale can be seen that may represent weight. A comet can be identified underneath the rainbow in the background. The comet may represent astronomy, and the rainbow itself may represent the wonders of light. In 1514, not much knowledge existed on these very different areas of science, and the angel representing us, humanity, may be frustrated with the lack of understanding of nature, as nature appeared in 1514. The scientific revolution initiated by Galileo Galilei and others has provided answers to many of these questions. In the 17th century, Isaac Newton explained the rainbow and documented this in his book Optics. An illustration from this book is seen here. Newton explains that the rainbow is the consequence of the passage of light through water droplets as they occur in a rainstorm. The light rays are first refracted on entry to the water droplet, then reflected at the back of the droplet, and refracted again on exit. The colors appear because the refractions depend on the color of the light. Newton's interpretation of light was not entirely correct. He tried to explain light as a stream of corpuscles, particles, and the experiment shown in figure 16 is his attempt to prove that this is the case and that light is definitely not of wave nature. He thought if light was a wave, white light could not be dispersed and then recombined back into white light, as he shows in this experiment. Building on the success of mechanics, where point masses interact with each other via forces, Newton tried to establish the theory of light in a similar fashion. In order to explain the refraction of a light ray when it passes from a rarer medium to a denser medium, he theorized that the light particles might interact with the boundary, and at the boundary change direction and speed. Because of his reputation, Newton's corpuscle theory of light persisted for a long time, although it cannot explain light phenomena like interference and diffraction. It is curious that despite its original failure as a theory of light, the particle aspect of light has found its way again into our modern understanding of light as a particle-wave dualism. Newton's particle theory of light was eventually surpassed by Christian Huygens' wave theory, established first in 1678. At the heart of Huygens' theory is the principle of linear superposition. Individual wavelets can superimpose to produce plane wavefronts. Not only can this explain what happens at the boundary between two media, the linear superposition of light wavelets also explains interference and diffraction. Light of a certain frequency can be assigned a wavelength lambda that depends on the propagation speed of the light in the respective medium. While Huygens' theory correctly describes the characteristics of light, it does not explain the nature of light. What is light? Our understanding of the nature of light goes back to 1865, when James Clerk Maxwell explained it. Maxwell had a lifelong interest in light, color, and photography. Together with his wife Catherine, he experimented on our perception of color. How do we see different mixtures of color? One of the few photographs of Maxwell shows him with his color top. The top was covered with different sections of colored cardboard and then spun to see how a person would perceive the result. Together with the photographer Sutton, Maxwell is also credited with the first ever color photography. This color photograph of a tartan ribbon is shown at the top right. Maxwell discovered the nature of light in developing his theory of electromagnetism, which was submitted in 1864 and then published in 1865. His theory showed that the nature of light is intimately connected to electromagnetic phenomena. Maxwell's theory of electromagnetism introduces four vector fields: the electric and magnetic flux densities and the electric and magnetic field strength. The theory is based on postulated differential equations. The modern form of these Maxwell equations was developed by Heaviside, Hertz and Gibbs in 1884 using vector calculus. Two of the equations involve the divergence operator, and the other two equations involve the curl operator. Each of the curl equations includes both the electric and the magnetic field. This coupling of the electric and magnetic fields is key to the understanding of the nature of light. How do the Maxwell equations predict light and explain its nature? This can be understood in a very straightforward way for the special case of light with a single wavelength that propagates harmonically through space. An example of this is a laser beam, for example the one shown here, the green light of a 520 nanometer laser. Concentrating on such a special case reduces the mathematical effort considerably, without reducing the physics inside. Taking the view that somehow light is related to electromagnetism, the four electromagnetic vector fields, if they indeed propagate through space, might also be harmonic with a fixed angular frequency. The time dependence of these vector fields may then be described with the cosine function, with the argument omega t. As usual, the angular frequency omega is defined as 2 pi times frequency f. In order to avoid the complicated algebra associated with the trigonometric functions sine and cosine, a clever mathematical approach is taken advantage of that does not affect conclusiveness. In this approach, all four vector fields and also the current density J and the charge density ρ are treated as complex numbers. Of course, the actual vector fields E, D, H and B are real numbers. Adding an imaginary part to this real number and treating the quantity as a complex number helps, however, with dealing with the time differentiation of those fields. It is important to keep in mind that the measurable information about the four vector fields is carried through the formalism as the real part of the complex number. Once a result has been obtained, the real part of that complex result can be compared with measurement. This approach is shown here as an example for the electric vector field. As discussed, we expect the electric vector field to have the form E0 times cosine omega t, whereby the cosine function contains the time dependence and the spatial dependence of the vector field is comprised in E0. Converting this real vector field E to a complex vector field E gives E0 times exponential function of I omega t. Here I is the imaginary unit I, equal to square root of -1. Taking now the real part of this complex vector field E gives again E naught times cosine omega t. Adopting this approach, the mathematical form of the four Maxwell equations remains the same. However, all quantities, apart from the position coordinates x, y, z, and time, are now complex. In particular, the four vector fields now have an amplitude that depends only on the spatial coordinates x, y, z, and a time dependence that is given by exponential function of I omega t. This means that the time differentiation of these vector fields is equal to I omega times the original vector field. Obtaining such a simple time differentiation simplifies the four Maxwell equations greatly. Substituting in the two curl equations for the time differentiation with I omega times vector field, we obtain this set of four differential equations. The equations have been simplified further by taking advantage of the two constitutive relationships. Electric flux density D is equal to permittivity times electric field strength E, and magnetic flux density B is equal to permeability mu times magnetic field strength H. Substituting in this way for D and B leaves us with four equations that only contain the electric field strength E and the magnetic field strength H. This set of four equations is still somewhat complicated because it contains the charge density ρV and the current density J. Since we are primarily interested in the propagation of electromagnetic fields as electromagnetic waves, and not so much in how electromagnetic waves are generated or how they may be received, we can limit the discussion to free space, where there are no generating source charges and no currents present. Since the relative permittivities are very similar, our discussions for vacuum also apply to air and the atmosphere. The focus of the discussion is illustrated at the bottom. Of course, there has to be a region in space somewhere where electromagnetic waves are emitted through time-varying charge and current distributions, but we are not looking at that region of space. Instead, we let the waves propagate into a region of free space where there are no charges and no currents. This region is indicated here by the red rectangle. In this region of free space, both the charge density ρ and the current density J are zero. This means the Maxwell equations become the set shown next to A. The divergence of both E and H is now zero, and through the curl equations, the electric field E is coupled to the magnetic field H. We want to show that the Maxwell equations predict electromagnetic waves, and in particular we want to show that they predict light. How do we set this up? Well, the Maxwell equations are fundamental and of general validity. If electromagnetic waves exist, it has to be possible to derive them from the Maxwell equations. Suspecting that the electric and magnetic field follow a cosine time dependence as shown next to B, we should be able to derive these wave functions from the Maxwell postulates just shown next to A on the previous slide. The first step in this derivation is the application of the curl operator to the first of the curl equations, equation 2. We obtain curl of E is equal to minus I omega mu curl of H. The curl of H can be substituted with equation 4, and we obtain further that the curl of E is equal to minus I omega mu times I omega epsilon E. Since I times I is minus 1, the minus sign in front of this term becomes a plus sign, and we finally obtain the equation curl E is equal to mu epsilon omega squared times E. This is a good outcome because it has removed the magnetic field H from the equation, and electromagnetically this equation is now decoupled. It only contains the electric field, E. In a second step of this derivation, we can take advantage of a vector identity, namely this one. Curl of a vector field is equal to the grad of the divergence of that vector field minus Laplace of the same vector field. Since this mathematical identity is valid for any vector field in vector calculus, it should certainly be valid for the electric field E. Vector calculus operations that involve two vector operators can be looked up in mathematics textbooks. They can, however, also be derived from this DCG chart. In this chart, D represents divergence, C the curl, and G the gradient. The chart is interpreted by following the arrow. For example, the divergence of curl means going from D via the blue arrow to C, and the result of that operation, as expected, is 0. Similarly, the curl of a gradient field is always 0. That's represented by the path from C to G, and next to this path is the 0, indicating that the curl of G is 0. In relation to our derivation, we are interested in the gradient of the divergence, so we follow the path indicated by the green arrows. We find that the gradients of the divergence of a vector field is equal to the curl of that vector field plus the vector Laplacian of that vector field. Rearranging gives curl of a vector field is equal to gradient of the divergence of the vector field minus the Laplacian of that vector field. The convoluted curl operation on the electric field can therefore be replaced by the gradient of the divergence of E minus the Laplacian of E. Since, in our case, the divergence of E is equal to 0, which is a physics argument, the first term of this expression is 0. The second term remains, it's minus Laplacian of E. So the negative Laplacian of E is equal to mu epsilon omega squared times the electric field E. It is instructive to write out the Laplacian in its three components. This has been done here for Cartesian coordinates. We can see that the differential equation in the red rectangle is really a system of three independent differential equations for each component of the electric field. The differential equation in the red rectangle is in fact a wave equation. This is obvious if that equation is rearranged as Laplace of E plus mu epsilon omega squared times E equals 0. The parameters mu, epsilon and omega squared can be combined as the constant k squared, which we interpret as the wave number square. This means in particular that k is equal to the square root of permeability and permittivity times angular frequency omega. The differential equation is a wave equation because the second derivative of the electric field E, as represented by the Laplacian, depends on the electric field E itself. Using the same approach and arguments as before, the same wave equation can be obtained for the magnetic field, with Laplacian of H plus k squared H equals 0. Writing down the Laplacian in its components, we can formally show that every vector component of the differential equation of the wave equation, Laplacian E plus k squared E, is separately equal to 0. This is also true for the magnetic field strength H. So far we have only assumed that the wave has a single frequency and that its propagation is harmonic. In order to limit the considerations further without affecting the general conclusion, we may decide that our waves are plane and transverse. That's illustrated here. The propagation direction of the plane transverse waves may be the z direction. That means the wave crests are parallel to each other as indicated. Uniform plane transverse waves that propagate in the z direction have amplitudes that do not change in the x or y direction. This means in our case that dx of ex equals dy of ex, and both of these differentiations are 0. Similarly, dx of ey equals dy of ey, and that is also 0. Furthermore, because it propagates in this direction, the wave has no field component in the z direction. Ez equals 0. Such a uniform plane transverse wave propagating in the z direction is visualized here. For any given point in time, the field strength is constant in the x direction and in the y direction. it only changes in the z direction. Since several partial differentiations are zero and the z component of the field is zero anyway, for plane waves, the wave equation for the electric field simplifies to two differential equations, which are shown here. dz squared of Ex plus k squared Ex equals 0, and dz squared of Ey plus k squared Ey equals 0. It can be readily seen that the most general solutions to these two differential equations are given by the functions in the blue rectangle. Both functions are sums of complex exponential functions with the argument I kz, or alternatively minus I kz. The plus and minus sign identify different directions of the propagating wave, since it may propagate in the plus z direction or into the negative z direction. Since we are at liberty to choose our Cartesian coordinate system, we can simplify this further. We turn the coordinate system about the z direction, the direction of propagation, until the y component of the electric field is always 0. This leaves us with only a function for the x component of the electric field, which is given by Ex plus times e to the power of ikz plus Ex minus times e to the power of minus ikz. We interpret the first term as a wave that travels to the left and the second term as a wave that travels to the right. This is the solution of the electric wave equation. Let us take stock. We have shown that the Maxwell equations yield wave equations for both the electric field E and the magnetic field H. They both have the form Laplacian vector field plus k squared vector field equals 0. K squared is equal to mu epsilon times omega squared. In order to achieve this, we have limited ourselves to single frequency waves of harmonic nature. We also require the waves to propagate in free space where there are no charges or currents. Requiring that our waves are transverse and plane, we have obtained a solution for the electric field. Using the same arguments, one can also show that the solutions for the magnetic field are given by the equations I and 2I. As with the electric field, the magnetic field only has components in the x direction and in the y direction. There is no z component. Since we have already chosen our coordinate system, we cannot turn it again to get rid of the hy component. We have to accept that the magnetic field might have two components, an x and a y component. It will, however, turn out that that is not the case. We will find that the magnetic field only has a y component. This can be shown by substituting the solution for the electric field in the Maxwell equation. Since the electric field only has an x component, the respective determinant operation gives us the vector 0, dz Ex 0. So only the y component of this curl vector is finite. The x and z components of the curl are 0. According to the Maxwell equation, this curl vector has to be equal to minus I omega mu times the magnetic field strength H. Since H potentially only has x and y components, we now find that the x component in fact is 0. The magnetic field vector only has a y component. Since the electric field only has an x component and the magnetic field only has a y component, we find that the two field vectors are at an angle of 90 degrees. It is thus clear that the electromagnetic wave equation can be solved if the electric and magnetic fields are perpendicular to each other, and the y component of the magnetic field, Hy, equals k on omega mu times the x component of the electric field, Ex. The two wave functions that solve the wave equation are shown in the large red box. Both functions have the same dependence with z as e to the power of ikz. However, the amplitudes differ. the electric field has the magnitude Ex plus, and the magnetic field has the magnitude Ex plus times the constant factor k on omega mu. Importantly, we recognize that the three important vectors are perpendicular to each other. The propagation direction is perpendicular to the electric field vector, which itself is perpendicular to the magnetic field vector. This confirms that electromagnetic waves indeed exist if they have this particular structure. But what does this have to do with light? The answer to this question is provided by the wave number k, which we have defined as the square root of permeability times permittivity, square root of mu epsilon, times the angular frequency omega. We also know that for any wave, it holds that wavelength lambda times frequency f equals the propagation speed of the wave, c. Substituting for k and frequency with 2 pi on lambda and omega on 2 pi respectively, we obtain equation 2 as c equals omega on k. Combining equation 1 for the wave number and this equation 2, we get the expression omega squared on c squared equals mu epsilon times omega squared. Taking the square root on both sides, we find that the propagation speed c is given by the square root of 1 over mu times epsilon. The permeability mu and the permittivity epsilon are fundamental constitutive parameters of electromagnetism. In the SI system of measurements, mu in vacuum is given as 4 pi times 10 to the minus 7 Henry on meter. Epsilon may be approximated as 1 over 36 pi times 10 to the minus 9 farad on meter. As we substitute in the square root, we find that 36 pi on 4 pi gives 9, and the powers of 10 combine to 10 to the 16. Taking now the square root, the result is 3 times 10 to the 8 meters on second. This is the surprising result. 3 times 10 to the 8 meters per second is the speed of light in vacuum. The two constitutive parameters of electromagnetism predict the speed of light. Only a few years before Maxwell developed his theory of electromagnetism, the speed of light had been measured in experiments carried out by Arago, Fizeau and Foucault in France. The photo shows a spinning mirror device used in those experiments. From those measurements, it was clear that the speed of light was 3 times 10 to the 8 meters per second. The fact that this propagation speed can be derived from Maxwell's equations of electromagnetism strongly suggested that light is an electromagnetic wave. The sketch shows a modern realization of the rotating mirror experiments carried out by the three Frenchmen. A laser beam is projected onto a rotating mirror Rm and reflected to a distant mirror Sm. On return, the rotating mirror has moved, and only for a certain rotational velocity the image of the laser beam will be projected back into the camera. If the rotational velocity of the rotating mirror Rm and the distance between rotating mirror Rm and distant mirror Sm is known, the speed of light can be calculated. Light therefore has all the properties of an electromagnetic wave in space. A laser beam of light propagates in the z direction because its electric field vector oscillates in the x direction. At the same time and in sync, the magnetic field vector h oscillates in the y direction. The existence of light was therefore the first confirmation of the correctness of Maxwell's theory, because other forms of electromagnetic waves were not discovered until 1887, when this was achieved by Heinrich Hertz. The principal setup that Hertz used is shown at the bottom left. With a Leyden jar and a coil, he produced a large voltage difference which discharged. This spark creates electromagnetic waves. Hertz achieved detecting these electromagnetic waves with an open receiving loop by observing tiny sparks at the endpoints. In comparing such experiments with theory, the real part of the electric and the magnetic field have to be considered. The corresponding real electric and magnetic wave functions are given in the red box. For a fixed time and plane waves propagating in the z direction, the functions are sinusoidal with the argument kz. The sign in front of kz identifies the direction of propagation. The amplitude of the electric and the magnetic field differ by the factor square root of epsilon on mu. A much more powerful realization of Hertz's experiment is that of a lightning strike, shown here. Of course, we see the light associated with the lightning propagating towards us as an electromagnetic wave. We can, however, also detect electromagnetic waves at other frequencies. Such a result is shown here. Two electromagnetic wave pulses are detected when electric field strength is plotted as a function of time. The first pulse is associated with the ground wave, and the second pulse is associated with the so-called sky wave. The sky wave comes about because the electromagnetic wave is reflected at the ionosphere, before it reaches the receiving antenna. The time difference between the two electromagnetic pulses is consistent with the speed of light of 3 × 10⁸ meters per second. We have verified that the Maxwell equations predict electromagnetic waves. In such waves, the electric field and magnetic field vectors are perpendicular to each other, and their oscillation is in sync in a right-handed sense. Normal to the plane that is spanned by the electric field vector and the magnetic field vector is the direction of propagation. In this direction, the electromagnetic wave propagates in vacuum at the speed of light of 3 × 10⁸ meters per second. This is also the propagation speed of light, which is an electromagnetic wave.